astronomy, optics and electronics, and he will be presenting the HAWC Gamma Ray Observatory, generating big data in Mexico.
Thank you, Salma. Thank you, Julie, for the invitation, in particular to Carlos Casasus, and it's a pleasure, always a pleasure to come to Puerto Vallarta, in this case to tell you a little bit about this observatory and the sort of data we are generating right now in Mexico. I'll show you a little bit, very briefly, about this collaboration, also about cosmic rays and gamma rays, how this observatory works, and a little bit about the development of the observatory in science and the data that we acquire, and then after me, Andres Sandoval will tell you more or less how is the handling of these data. Just a very brief advert. I come from the Instituto Nacional de Astrofísica Óptica y Electrónica. This observatory is the successor, is on the same grounds of the Observatorio Astrofísico Nacional, founded in the late 40s by Luis Enrique Erro, with the support of the Harvard University. And in 1971, it was transforming the institute in the Instituto Nacional de Astrofísica Óptica y Electrónica, and we started with developing the Carramiñana Observatory, which has been in operation since 1988. And nowadays we work in developing observatories, working with this sort of data, doing optics for different projects, electronics, then spillovers like cryogenics, telecommunications, and robotics. Slightly more related to the topic is that we have been working now for 20 years in the development of the Gran Telescopio Millimetrico Alfonso Serrano on MTGTM. This is a collaboration with the University of Massachusetts at Amherst, and basically is to build the largest single-dish millimeter telescope in the world. It's a 50-meter antenna, and this is to operate in the 0.4 to 4 millimeter, 0.8 to 4 millimeter band for astronomical observations. This is on top of Sierra Negra at close to 4,600 meters altitude, and INAOE has been working on developing this site since 1997. The telescope is currently operational. And we're here at the top of Sierra Negra, or Tepetl, which is now for Black Mountain. As I mentioned, well, in fact, it's about 14,000 feet. And next to the tallest mountain in Mexico, Tepetl, at 5,600 meters altitude, which provides gorgeous views from the site. We, from the city of Puebla, we drive basically 1 hour on the road that takes you from Mexico City to Puebla to the coast in Veracruz, and then 1 hour up to the top of the mountain. This valley here is at 4,100 meters altitude, and that is where we are developing the high altitude water Cherenkov Observatory, which is a wide field cosmic ray and gamma ray observatory that works for both particles and electromagnetic radiation in the 100 giga-electron volt to 100 tera-electron volt energy range. We're clearly not doing this by ourselves. We work together with several institutions, with 4 of the institutes at the UNAM National University. In particular, Andres Sandoval is at the Physics Institute. Lucas Neyland, also part of the collaboration, is at the Instituto de Ciencias Nucleares, or with the University of Puebla and several institutions more. In the US, this is a binational collaboration of about 30 institutions. University of Maryland has been leading the effort, and Los Alamos National Laboratory. They have worked with the 2 grants from National Science Foundation, Department of Energy, from the side of Mexico. HAWC is supported, aside from the institutions, by the CONACYT. And this is a picture of the meeting of HAWC collaboration, October 2014, at the University of Puebla. So one of the subjects of our study, and in fact the underlying one, is a topic that has over 100 years, which is the cosmic rays. These were discovered in balloon flights. So there was, since the discovery, the high altitude aspect of them was clear. They were clearly seen by Victor Hess when he went up to balloon flights up to 5,000 meters altitude. And these are highly energetic particles that have energies well in excess of giga-electron volts compared to, say, 3 electron volts of visible light or 1,000 electron volts of X-rays. They're mostly charged particles, charged atomic nuclei. Most of them are protons. Some are alpha particles or heavier. They travel chaotically because basically their trajectories are curved because of the magnetic field of our galaxy. Their curvature radius is less than 1% of the typical distance between celestial objects. So they carry no information of their origin, and they basically come isotropically also something like that. So, I mean, what's the origin of the cosmic rays is a question that has about 100 years. In open, the Fermi proposed particular supernova explosions as the origin of these ones, and one thing that that has been postulated is that cosmic ray, the production of cosmic ray particles must be come together with the production of gamma rays. So in a way, if you study gamma ray sources in the sky, you will also study cosmic rays and study both things. So gamma rays are the most energetic form of electromagnetic radiation. So as I mentioned, visible light is just a couple of electron volts, and here we're talking of one linkage. This will be billions of electron volts to trillions electron volts. Part of this is more or less a very simplistic cartoon view of how astronomy is made. Some of it is from ground-based, higher altitude places or lower altitude places, or from space. And what is remarkable in the case of HAWC and instruments like atmospheric Cherenkov telescopes is that what you are observing from the ground is the effect of a single particle or a single elementary particle or photon from the atmosphere, and that is measurable from the ground. So a little bit in detail, part of gamma ray astronomy is made from satellites, say from the mega electron volts to, say, 100 giga-electron volts can be done from space. Fermi Gamma Ray Space Telescope is right now what is breaking ground on this topic. And once you're in from the, say, basically 100 giga-electron volts to above, you can do it from the ground. And the way you can do it is because high-energy particles that arrive to the atmosphere, they don't reach us, unfortunately, but they collide with atmospheric nuclei. They produce charged pions, and these produce a cascade of secondary particles, 5,000s of these, or even millions of these, that can reach ground, especially if you locate these things at high altitude. The same applies for gamma rays that produce a positron-electron pair. These radiate more gamma rays, like Greenwich travel, always sharing and diminishing the energy until this cascade of particles is not able to continue and it starts spinning. So if you want to detect directly the particles on the ground, it is good if your ground is as high as possible. And the method of detection of these charged particles, many of these are either electrons or muons. In the case of cosmic rays, you have muons. In the case of gamma rays, it's basically electrons, positrons. Is through the effect of Cherenkov radiation. So if a particle moves faster than light in a medium, like air or like water, then it will emit Cherenkov radiation in either air or water. And the condition is basically that its speed is faster than the speed of light divided by the refraction index of the medium. basically in water, the refraction index is like 1.3, so you don't need a very energetic particle in order to already see chunk of radiation. This, in fact, happens in fusion fission reactors in nuclear reactors. So you can see the water, the particles that are in these reactors, they emit chunk of radiation. And these cascades, basically, they extend for at least over 100 meters or more, much more, depending on the energy of the primary particle. And since at least 50 years, they have been studied with arrays of detectors put on the ground. So, for example, Haverhill Park in the 60s and 70s was the first of these sort of arrays to use water to detect just cosmic rays. In the 80s, the Cygnus array was located, was the first effort to locate these things at some altitude, 2,100 meters, not too different from, I was going to say, from where we are, we're at sea level right now, sorry. and then both the Milagro Observatory was the first one really to do some gamma ray astronomy, and the trick here is to distinguish gamma rays from cosmic rays, and I'll show very quickly. So this is more or less how the Milagro Observatory looked. That was in New Mexico, 2,600 meters altitude, a latitude of 36 degrees north. And basically what you have is like a pond of water, about 50, 80 meters. I'll show the cross section the next slide. Surrounded by also individual tanks of water, and each of these tanks had one photo multiplier tube, and here there were about 700 of those photo multiplier tubes to basically sample the arrival of these particle cascades on the ground. It was operational from 1999 to 2008 when it was shut in order to recycle part of this material in the HAWC observatory that is now operational in Mexico. Particles and photons detected here had typical energies of about 40 tera electron volts, and HAWC sees particles of much lower energy. Here you can see this is the array of photomultiplier tubes that was put on 2 layers. The shallow, well, the deep part was 50 meters in length, the top part was 80 meters. And when you have the particles reaching the water, basically you have the emission of this chunk of water, this chunk of light in water. The detector is kept dark, so that means that you can basically operate continuously, day and night, and you receive showers that can come from any direction. Basically, as you time the arrival of particles in the water here, you can more or less see from position where in the sky these cascade was originated, and hence the source of gamma rays. So I'm not going to go too much in detail. With Milagro, I will say that once Milagro got the first results and was able to do actual gamma ray astronomy using the water Cherenkov technique, there was this proposal to make something bigger, basically something higher, about 4,000 meters. That was let's say, the specification. And the HAWC observatory is also closer to the equator. We're at 19 degrees north latitude, so we can see more of the sky, and it's an improved design. I will not go too much into detail, but basically at one moment we see about 15% of the sky continuously, what is on the zenith of the HAWC site, which is also the LMT, very close to the LMT site. And as the day progresses, every sidereal day we cover 2/3 of the celestial sphere, so we're pretty good at doing continuous daily mapping of the sky in gamma rays. So this is view from the highest point in Mexico. If you are able to climb to Pico de Orizaba, you will see the large millimeter telescope Alfonso Serrano here, and here you will see the HAWC observatory some 500 meters below it. You won't see it like this because now we have basically finished its construction. This observatory is made of 300 individual tanks, water tanks, water Cherenkov tanks, and they're instrumented each with 4 photomultipliers. 3 come from Milagro, and 1 more was acquired with the support of Los Alamos National Observatory. The whole observatory covers about 22,000 square meters, and the idea, in order to match or to be able to have some overlap with what is observed from the space, is to have it as dense as possible. So basically, one is a muon or electron that penetrates the water, emits Cherenkov radiation, and you have these 4 photomultiplier tubes. These are the Milagro ones, the ones that were in New Mexico from 1999 to 2008, and these ones, the ones acquired with the funds from NSF. Each tank is connected to what's called the counting house, which is where we receive the data and where we control the whole experiment. The tanks are made of corrugated steel. These are sheets of steel, and you can see more or less the process of building it. This comes like in leaves, and you basically make rings. First we dig here. You have these jacks to basically make a ring, lift it up. So you first make the upper part, then next one, next one, next one, and that's how we build the 300 tanks. This is 60 minutes. Okay, good. Inside of each of these tanks, there is a plastic bag that is opaque to light. So basically, the phototubes are in light isolation, and these are tested here in this lab that is next to the HAWC observatory. The first stage was to prove that we could basically build an extensive array from these. So we built an engineering array called VAMOS in around 2010. It was basically 7 tanks, these 6 together, one a bit further apart. And in April 2011, the first data, that was a small data, from HAWC was acquired with a coincidence of these 7 tanks. But basically, this experiment rapidly started generating lots of data one of the things of VAMOS was to prove that we could make cosmic ray maps of the sky, and that we had the techniques to separate gamma rays from cosmic rays. But at the moment, VAMOS was not big enough really to do astronomy, but we could do cosmic ray maps. And for example, this feature up here is a real feature, is not noise. 2012, we started the construction of the array. Basically, this is where we conflate the bags. By October, September 2012, we had the first phase. This is HAWC 30, looked in Google Earth. And HAWC 30 was already able to produce the first results, like the observation of the shadow of the moon on cosmic rays, and first gamma ray map, still not deep enough to detect sources. HAWC 100 was already much more prominent. So being larger, it was already able to discard gamma rays from cosmic rays. That it started continuous operation in August 2013, and that has provided the first, let's say the first Skylab with the detection of gamma ray sources that we have. Basically, this is where we conflate the bags. This is where we purify also the water. The water has to be transparent in order for us not to lose the gamma ray signal. This is the counting house. This is where all the electronics and the data acquisition system is present. And I'll show you some of the information that we have to retrieve from the data. Basically, we have timing information. So we time to time with an accuracy of about 1 nanosecond, relative 1 one tank to another. And in fact, here you can see the scale. It came first where it's in blue, then later it went this side, so that's telling us that the shower front, the particles came that way, and that's one part of the data that we have to record. Another data that we have to record is the energy deposit on each tank, basically, that allow us to characterize the event, whether it comes from a gamma ray, or primary, or a cosmic ray. And in fact, just to put in numbers, HAWC gets about, here must be here, 15,000 cosmic rays per second continuously all day, day and night. And of these, there are about 400 that are gamma rays from the brightest object in the sky, the Crab Nebula. So we are getting about a billion events per day. Each event we need to have the timing, the signals for the 1,200 channels, and the collective signal of the added signal of these channels. And we also have extensive monitoring data of each tank, for example, its voltage and how it's doing. So we're generating around between 1 and 1.5 terabytes of data continuously. And this is a bit too much for the connection we have. This is display how we are. This is at the LMT. From the LMT, we have an optical fiber that can carry 10 gigabytes per second to Atizipla. HAWC is now connected also to this server in the town of Atizipla. From here, some years later, we could buy about 20 kilometers of fiber to get to Ciudad Cerdán, where we are connected through a commercial internet provider to the world. We also have optical fiber that goes outside of Ciudad Cerdán and connect us to the network microwave connection to the state of Puebla, which is supposed to give 300 megabits per second, but it gives more like 30, which, if you make the math, that's just not enough for us. Not only that, it's not enough for HAWC, but also this connection is shared by also the LMT telescope and other users on the site. Very quick, to show some results. HAWC, with 111 tanks, is able to detect very clearly the shadow of the moon, signal to noise over 25. That helps to characterize the performance of the instrument. We have detected the anisotropies of cosmic rays. I told you these were isotropic, but not quite. There is anisotropies of the order of a fraction of a part in 1,000, and basically these are indicative of either inhomogeneities in the magnetic field close to Earth or a nearby cosmic ray source or event. HAWC is able, with the information of how the particles are distributed on the ground, we're able to discriminate gamma rays effectively from cosmic rays, and right now we have already made a sky map that after 10 months more or less of operation is as deep as the one made by the Milagro Observatory after 8 years. Here we have the detection of the Crab Nebula, an active galaxy, sources in the galactic plane. Okay, just finishing, just a view of how we were building on Thanksgiving Day. That's Thanksgiving Day. We went from the HAWC 111 to 250 tanks operational in preparation to finish the observatory. December, we installed the last tank. We were all very proud of it. The array was fully connected in March last month, March 2015. Here you can see a view just on the 13th of March, just a week before the inauguration. This is Enrique Cabrero, France Cordova, at the top of Sierra Negra, 4,100 meters for the inauguration of the HAWC Observatory on Equinox Day this year. Just including our data is valuable not just by itself for the study of gamma ray sources just of the gamma ray emission, but we were also coordinated our research with X-rays telescopes on space, with the Fermi Observatory that observes gamma rays on lower energy, with Cherenkov, atmospheric Cherenkov observatories, with neutrino observatories, and also with gravitational wave detectors in order to join collaboratively with them. And the final slide is some data that we get also from the mountain, which are the views of Pico de Orizaba through webcams they make. Thank you very much.